Jnanam paramam dheyam. Knowledge is supreme.
So, let us look at one example to completely understand the process. So, we are given this matrix A. Okay. So, we want to find the eigenvalues and a basis consisting of eigenvectors to diagonalize this matrix A, if possible, right. So, what is the first step? Find the eigenvalues. So, look at determinant of A minus lambda I. So, A minus, so along the diagonal you will be subtracting lambda. So, here it will be 1 minus lambda, 1 minus lambda, minus 2 minus lambda, everything else remains the same. Find determinant of that. So, just written the answer here, it comes out minus lambda times lambda square minus 9, that means lambda is equal to 0 and lambda equal to plus 3 and minus 3. So, lucky here we have got 3 distinct eigenvalues, right. So, obviously, because there are 3 distinct eigenvalues and matrix is of order of 3 cross 3 and each eigenvalue is going to give you a eigenvector, and eigenvectors corresponding to distinct eigenvalues are linearly independent. So, for each eigenvalue we will find a vector which is eigenvector, put them together, they will form a basis of consisting of eigenvectors. So, that also will give me the matrix P which is going to diagonalize, right, because we are lucky here we have got 3 eigenvalues for 3 cross 3 matrix. So, let us just go through the process. For lambda equal to minus 3, so what will be the matrix we will be looking at? A minus lambda I. So, lambda is minus 3, so it becomes A plus 3I, right. So, that is the matrix. And how do you find the null space or nullity? You have to reduce it to the row echelon form. So, we are given here the row echelon form is given by this. Okay. So, once that is the row echelon form, what is the rank of the matrix? Rank of the matrix is 2. So, what is the nullity? 1, right. So, the eigenspace or the null space for this has only got dimension as 1. So, how do you find that? So, you will find from here, right, x2 minus x3 is equal to 0, right. So, x2 is equal to x3. So, you can give any value you like, right. For the vector which does not have a pivot, right, that what does that give me? X3 equal to 0 anyway, sorry, x1, the first one is x1, x1 is equal to 0. So, 0 1 1 is an eigenvector, clear. Once you have gotten the reduced row echelon form, writing down the basis for the eigen subspace or basis for the null space is quite easy. So, for the eigenvalue lambda equal to minus 3, 0 1 1 is an eigenvector, right, or you can also say the null space is spanned by this vector, scalar times this also will be an eigenvector, right. So, for lambda equal to minus 3 we have found. Let us go do for lambda equal to 3. So, lambda equal to 0. So, what will be lambda equal to 0? A minus lambda I, that is a matrix A itself, right. So, that is a matrix, and if you make it row operations it becomes like this. Okay. So, each again and again you have to look at A minus lambda I, reduce it to row echelon form and see what is the dimension and find the basis. So, again the rank is equal to 2, non-zero number of rows is 2. So, nullity is 1. So, dimension is equal to 1, right. I will have only one eigenvector which spans this. So, how do you find that? What is x2? From the second equation, x2 plus 0, x1, x2, x3 equal to 0. So, what is x2? 0. So, you get 0 here. What is the first equation? x1 plus 2x1, 2x2 minus 2x3 is equal to 0. Which one gets the arbitrary value? x3. Everything else is determined in terms of that. So, x3 you can give the value 1 just to be simple, right. So, give it 1 and compute x2 is 0, compute x1. So, you get the vector, right. Pivotal variables are computed in terms of non-pivotal, right. Non-pivotal variables, pivotal variables are computed in terms of non-pivotal variables. So, arbitrary values are given to the non-pivotal variables. So, here x1 plus 0 x2, right. So, we got x2 equal to 0, that is computed because there are, right, and the first one, the non-pivotal variable x2 is already determined, the non-pivotal one is x3, which can be given arbitrary value. So, that arbitrary value we have given it as 1 and found everything in terms of that. So, that is one eigenvector for the eigenvalue lambda equal to 0. So, let us do the same for lambda equal to 3. So, lambda equal to 3 a minus lambda I. So, that is a minus 3I, right. Again same process. So, if you so this is already in that. So, if you do the row equivalent form, this comes out to be this. So, what is the rank again? Rank again is 2, nullity is again 1. You see, we have got 3 distinct eigenvalues. So, rank of each null space is going to be 1 anyway, it cannot be more, right, because each vector is going to be there and they are going to be linearly independent. So, if you are getting something else, then you are making a mistake in your computations. So, again, so for here you get x3 is equal to, the second equation gives you x3 equal to 0. So, that is equal to 0. In the first equation x1 minus x2 plus x3 is equal to 0. x3 is given the arbitrary value, x3 has been determined, x2 is given the arbitrary value. So, x2 x3 are known, x1 can be computed from that, right, because this says x3 is equal to 0. So, x3 is known, and from the first equation x3 is known, x2 is given as the arbitrary value, that is a non-pivotal variable, and x1 is determined in terms of x2 and x3. So, that gives you 1 0 0 1 1 0. Okay. So, once you have got the 3 eigenvectors, right, you can write them as the columns. So, that is your matrix P or X, whichever way you want to call it. Okay. So, the first eigenvector, second eigenvector and the third eigenvector, okay, as the columns. I think there is a mistake here, right, this V3, this should be 0 here, right. So, once that is done, you check that x inverse Ax is equal to this, or simply Ax is equal to x times diagonal. If you do not want to compute x inverse, you can just verify that. Okay. So, it is clear. How do you find, given a matrix, to see it is diagonalizable or not? First step, find eigenvalues, characteristic polynomial, and see what are the roots. If all roots are distinct, you are lucky, you will find eigenvectors for each. Write down the columns of the matrix as eigenvectors, and you get a matrix P which is invertible, which will diagonalize it. If not, you have to see whether you are getting as many independent eigenvectors, the nullity is same as the algebraic multiplicity of that eigenvalue. If that is the case, again you are lucky and you are through, right. If not, it is not diagonalizable, right. Okay. So, another example. Okay. I want to do many examples, so that is very clear what we are doing. So, A is the matrix given like this, 3 0 0 minus 2 4 2 and minus 2 1 5. So, how will you write the characteristic polynomial? Diagonal entries becomes 3 minus lambda, 4 minus lambda and 5 minus lambda, everything else remains the same, A minus lambda I, right. So, write that, find determinant of that matrix. Okay. So, you can expand by any row or column, but because here are zeros coming, so it is good to expand it by the first row itself. So, 3 minus lambda multiplied by this goes, this multiplied by this. So, that minus 2, right, and simplify, it comes out to be this. So, that means what? If that is the characteristic polynomial factorized, that means lambda equal to 3 is an eigenvalue and lambda equal to 6 is another eigenvalue. So, this matrix has got only 2 eigenvalues, it is 3 by 3, it has got only 2 eigenvalues, and the root lambda equal to 3 is repeated. right. That means the eigenvalue lambda equal to 3 has got algebraic multiplicity as 2, lambda equal to 6 has got algebraic multiplicity equal to 1. Total of algebraic multiplicity has to be equal to the order anyway, because they are the roots of that degree, right. Okay, so that has algebraic multiplicity 1. So for lambda equal to 6 there is no problem, because only one solution is going to be there which is going to span, right, dimension is going to be 1. So we can do that process. We will have to see for lambda equal to 3 what happens, what is the null space. We have to find the geometric multiplicity of the eigenvalue lambda equal to 3. If it is 2, then we are lucky, then we can diagonalize. If not, then it is not diagonalizable. So let us check what happens. So lambda equal to 3, so A minus 3I, so that is this matrix, and you reduce it to row echelon form, that comes out to be this, right. Again and again since beginning, the only thing which is playing a role is how to make a matrix in the row echelon form or reduced row echelon form. If you know that, there is nothing much in the course as such, other than understanding the concepts. Okay. So what is the dimension of this? Sorry, what is the rank? What is the rank of this matrix? A minus 3I, the rank is 1, because only one non-zero row, right. So that means what? Nullity is equal to 3 minus 1, that is 2. So we are lucky, nullity is 2. That means we should be able to find 2 linearly independent eigenvectors for this eigenvalue lambda equal to 3, because the reduced row echelon form or row echelon form says its nullity is 2, right. So how do you find that? What is the process of finding all solutions or linearly independent solutions for the null space? What is the pivotal variable? 1, x1, x2 and x3 will get arbitrary values. So the idea is you give x2 and x3 arbitrary values so that they become independent, right. So one choice is give x2 equal to 1, x3 equal to 0, one choice, and find x1, and the other choice is give x2 is 0 and x3 equal to 1 and find out x1 in terms of that. Those will automatically become linearly independent. So that is what we do. So rank is 1. Okay. So what is the null space? You can give x2 and x3 arbitrary values, right. That is what we said, x2 and x3 arbitrary values, and find x1 in terms of x2 and x3. So that is how you write. It consists of all vectors of this form where x2 and x3 are arbitrary, right. That is writing the null space. And to find the basis, so this gives you the dimension is equal to 2, and find the basis. So you give first x2 equal to 1, x3 equal to 0, and second choice x2 equal to 0 and x3 equal to 1. So once you do that, you will get x1 and x2. You get 2 eigenvectors for the same eigenvalue lambda is equal to 3, and they will automatically be linearly independent. You can just check anyway, but it is not an issue at all, because we have already done these kind of things. So these two are linearly independent. So we have got 2 linearly independent eigenvectors for the same eigenvalue lambda. For lambda equal to 6, we are going to get anyway one eigenvector. So we got 3 eigenvectors which are linearly independent. So matrix will be diagonalizable. Okay. So let us compute that. So A minus 6I, so that gives you this. So its rank is equal to 2, as it should be, because it is an eigenvalue and multiplicity 1, it can't be more than 1, it has to be something at least 1. Okay. So and what, how will you get the solution? x2 minus x3 is equal to 0, x3 will be given as the arbitrary value and x2 determined in terms of that, right. And those two values when you put here, you get the value of x1, but anyway x1 gives you x1 everything equal to 0, so x1 is 0 anyway from there, right. The first equation gives you x1 is equal to 0. So you get the eigen subspace corresponding to that is 0 alpha alpha when you put that value, Okay. Alpha is equal to, right, is it clear, x2 minus x3 is 0. So, x2 is equal to x3, right. So, you put the value equal to alpha, you get x2 equal to alpha. So, you can make a choice, you can take any alpha you like, right, this is a span, right. So, one eigenvector which will, so all you is a one dimensional. So, any vector non-zero vector will span. So, let us take alpha equal to 1. So, 0 1 1 is an eigenvector for the eigenvalue lambda equal to 6, right. So, once that is obtained, we have got 3 eigenvectors corresponding to 2 eigenvalues, but they are all linearly independent. So, we get the matrix, the first one eigenvector, the second and the third, put them together, you get the matrix P. Determinant of this is not 0 because they are linearly independent. You can check also. So, it is invertible and P inverse A P should be equal to the diagonal. This is again a mistake here, that should be 3 3 and that should be 6, the third eigenvalue, right. So, check. So, you can check whether computing P inverse, you can compute P inverse A P and see it comes out diagonal, or A multiplied by P is same as P multiplied by the diagonal matrix, right, 3 3 6. So, either way you should check. So, that is verification of that actually you are getting a diagonal matrix. It's clear, diagonalization process, everything clear to everybody? Yes.